Now that we've derived a functional form for the Gibbs energy of an ideal gas mixture, we can then calculate the chemical potential of that ideal gas mixture, because we know by definition it's just the partial derivative of the Gibbs energy with respect to the moles of one of the molar species. So let's plug in the equation we derived in the previous video. NiHi Ig minus, and I'm going to kind of multiply across the moles. I equals 1 C NiLn 1 C here. Okay, so now we're going to take the partial derivative of it. For the enthalpy and the entropy terms, essentially, remember, this goes from I equals 1 to C. So the only non-zero derivative is the case where your I, or I guess maybe it's better if I call these J's. In any case, the only non-zero derivative is the case where J is equal to I. Alright, and so everything else will drop out except the ith term. And so once again, this enthalpy is a function of temperature for the ideal gas. The entropy is a function of both temperature and pressure. Here, the derivative is here. The first, we're going to have to apply the product rule. So the first derivative here, we'll get back out ln of Ni over N total, which is just the mole fraction. So RT ln of Yi. But then we're going to have to take the derivatives of the stuff inside the natural log. And so our derivatives end up looking like this. Plus, I guess this RT is on the outside of everything. Ni over Ni here. And here we have the summation of Ni over summation of Ni over the total Ni. Kind of a weird way to write it, but in any case, what we get here, well, first of all, this thing here is just 1. And here we're essentially calculating the mole fractions and then adding up all our mole fractions. So that's also going to be equal to 1. And so we're going to get 1 minus 1, and those both go away. And so our chemical potential is going to be equal to Hi minus Tsi for the ideal gas plus RT ln of Yi. The H minus Ts over here, this once again is just the definition of the Gibbs energy. So we could combine those terms. So we have the Gibbs energy of the ideal gas plus RT ln of Yi is equal to our chemical potential. Right? Okay, so we gained some insight, but there's still one more sort of kind of weird term here, which is the Gibbs and molar Gibbs energy of the ideal gas. So we kind of want to get more insight into what that is and how it's affected by various parameters. To do that, let's think back to chapter 6. actually looked at our Gibbs energy, and we saw that for ideal gases, the molar Gibbs energy can be described like this, where it's some reference state molar Gibbs energy plus the integral of V molar dP from some reference pressure to some final pressure. Okay, that's just how one would get the molar Gibbs energy. Now, if we remember that we're dealing with an ideal gas, we know that the molar volume is equal to RT over P. Right? And so in our integral, we would just be integrating dP over P. And in the end, what we get is GI ref plus RT natural log of pressure over P ref. Okay? All right, so that's what, to get this, which is in our chemical potential equation, we just plug in this. So the chemical potential of a species in our ideal gas mixture is just going to be the reference molar Gibbs energy for that species in an ideal gas plus RT, and we have a RT natural log of Yi in the original chemical potential equation. But when we plug in for this, we're going to have another natural log term. So we could combine them. So now we get Yi P over P ref. And we know that this is just equal to the partial pressure. So the chemical potential of a species in an ideal gas mixture is just the molar Gibbs energy of that species at the reference state plus RT natural log of Pi over P ref. Okay. Commonly, you'll also see this term in various textbooks and in the literature, also referred to mu I at the reference state. Just letting you know, these are the same things. So they're just referring it to different, using a different nomenclature.